the TCPIP model, or the Internet Protocol Suite, or the DoD model, all names are the same. It is just like the OSI model, a conceptual model, shows us how our end-to-end data communications work. We have these in place to ensure that we have a standardization of how data should be packetized, addressed, transmitted, routed, and received, regardless of what our backend systems might be. Where the OSI model has 7 layers, the TCP/IP model only has 4. From the lowest layer to the highest layer, you can see a comparison here below how the TCP/IP model is mapped up towards the OSI model. This is the model we mostly use today, but many people still refer to the OSI model, so you need to know both. The link and physical layer is the lowest layer. It has all the communication that we send and receive within a single local network segment, and it spans both the physical and the data link layer on the OSI model. Layer 2, or the internet network layer, maps directly to the network layer on the OSI model, which is IP connections between networks, providing, well, internet walking. The transport layer, or layer 4, is actually the same on both the TCP/IP model and the OSI model, and handles the host-to-host communication. Remember, that's where UDP and TCP were. And then finally we have the application layer, and it combines layer 5, 6, and 7 from the OSI model. And it provides process-to-process data exchange for our applications. I'm going to go over the TCP/IP model a little less, since we've already covered much of this in the OSI model. And remember, these are logical models. They just provide an easier way of us to understand how networks work. So on the link and physical layer, we have exactly the same we would on the OSI layers 1 and 2. We have our MAC addresses, we have our cables, we have our physical devices, and all our data contained to host on the same network. That will be host on the same subnet too. The internet network layer is the one that maps directly to OSI layer 3, networking layer. This is where we add in our IP addresses. An IP has 2 basic functions. First one is the host addressing and identification, where each node has a unique IP address so we know where to send the data, and then it does packet routing. We also talked about that earlier, where we used the example of an ISC² server. I want to go to the website. In my browser, I type in isc².org. That's then translated to an IP address and sent off into my service provider's network. For each router it hits, it checks against the routing table, seeing what's the best path to the ISC² website and their IP. Then it's routed through the network, it reaches the ISC² website, the server sends back my request for the website, and again it's routed through all the routers, finding the best path to get back to my IP. Layer 4, or the transport layer, was, well, on the OSI model, the transport layer. So that one's an easy one to remember. This is where we have TCP or UDP. This is also where we have port numbers. Port numbers are very important and we'll cover them more later, but an easy way to think of them is I don't just go to a website. I go to a website and a port number, and then it replies back to my computer with an IP and a port number. So if I go to the ISC² website, what I'm really requesting is ISC², that's translated into the IP address, and since ISC² is a secure website, it'll be port 443. On my end, it will send it back to my browser, but I might have 20 browser windows open on different websites. So to ensure that it delivers it to the right browser window, use port numbers. Easy way to think of port numbers and IP addresses is kind of like a house with a bunch of apartments in it. The IP address is the house itself, the whole building, whereas the port number, the specific apartment number. There could be hundreds and hundreds of apartments in the building, so you need both the building and the apartment numbers to get the delivery to the right place. Layer 4 on the TCP/IP model is the application layer. And remember, it spans layer 5, 6, and 7 on the OSI model. The application layer has all the protocols used by our applications to provide the user services or exchange data over our networks. And the type of applications and the protocols we use determine how the data is transported in the lower layers. If our application is voice over IP, the transport layer needs to know that and then chooses to send it as UDP traffic, whereas if it's a website, it'll also be told that and then send the traffic as TCP traffic. Routers and switches don't normally inspect the packets they send, they just provide the conduit to send it efficiently and fast. We can, however, use firewalls or bandwidth throttling to interpret some of the application data. What that really means is we can prioritize our data, and to some extent the firewalls that are below level 5 can inspect traffic that's not encrypted, but if the data itself is encrypted, it can't really see what the data is. It's also important to remember that the TCP/IP model distinguishes between user protocols and support protocols. User protocols are the protocols we use, support protocols are, well, support protocols. They make stuff work. Over here on the right, you can see a very simplistic way of looking at how packets travel through our network and the headers that are added for each layer. The green box in the middle is the actual data. Then on the application layer, we add the upper layer headers. This is where we tell it's a website, it's HTTPS. Then at the transport layer, the TCP or UDP header is added, the port number, so since it's a website, we get a TCP header, and since IC2 is secure, it's port 443. Then on the internet network layer, we add the IP header. What's the source and destination IP? Where do we need to go get the data, and where do we need to send it? On the link layer, we add a layer to header and footer, and then finally at the physical layer, send all the actual data, the zeros and the ones, which the server then receives, and the further up the stack we go, the previous layer is removed. When we get to the internet network layer, it removes the layer 2 header and footer. And the transport layer removes the IP, the application layer removes the TCP header, and so on, all the way up to the application where the data is received, and then it goes the other way back. Since the packet we sent had a source and destination IP, those are just reversed. It goes through the stack again, adds all the headers, we receive it, we remove all the headers, and the website shows up on our computer. So for each layer of the TCP/IP model, we either add or remove the encapsulation. It's called encapsulation or decapsulation. And the higher up the stack we go, the slower and the smarter the stack is, exactly like the OSI model.